National Electrical Code, or NEC, doesn't offer a specific definition for the exact starting point of an emergency system. However, interpreting Section 517.30, we can understand that the emergency system encompasses all components and wiring essential for supplying backup power to critical loads during a normal power outage. Effectively, the system starting point is where the normal power source is interrupted and the emergency power source connects to power those critical loads. Considering a critical branch transfer switch scenario with feeds from both the normal power supply and the generator, the emergency system originates at the line side of this transfer switch. This is because the transfer switch is the mechanism that disconnects the normal power supply and connects the generator power to the critical loads. Section 517.30c3 dictates mechanical protection requirements that extend to all parts of the emergency system. This includes wiring and cables, conduits and raceways, boxes and enclosures, transfer switches and generators. It is important to ensure that all components from the line side of the transfer switch to the critical loads have the necessary mechanical protection. To clarify, consider these points regarding mechanical protection. Firstly, all wiring and cabling associated with the emergency system must be adequately protected from physical damage. This means using appropriate conduit, cable trays, or other approved methods to safeguard the conductors. Secondly, conduits and raceways must be installed in a manner that prevents damage from impact, abrasion, or other external forces. This includes using proper supports, fittings, and burial depths where applicable. Thirdly, all boxes and enclosures housing emergency system components must be constructed of durable materials and installed in a way that protects the contents from physical damage and environmental factors. Fourthly, the transfer switch itself must be protected from damage, either through its design and construction or through supplementary protective measures. Fifthly, the generator supplying emergency power must also be protected from physical damage and environmental factors. This may involve housing the generator in a dedicated enclosure or providing other forms of protection. It is critical to thoroughly assess the specific installation and identify any potential sources of physical damage to the emergency system components. Based on this assessment, implement appropriate mechanical protection measures to ensure compliance with Section 517.30c3 of the National Electrical Code. Now let's delve deeper into some specific aspects of emergency systems and mechanical protection. Firstly, conduit selection. The choice of conduit material, such as rigid metal conduit, intermediate metal conduit, electrical metallic tubing, or rigid polyvinyl chloride, depends on the specific application and environmental conditions. For example, rigid metal conduit provides excellent physical protection but may be more expensive and difficult to install than electrical metallic tubing. Secondly, cable types. When using cables instead of conduit, select cable types that are specifically listed for the intended application and provide adequate mechanical protection. For example, metal-clad cable offers superior protection compared to non-metallic sheathed cable. Thirdly, burial depth. For underground wiring, adhere to the minimum burial depth specified in the National Electrical Code to prevent damage from digging or other activities. Typically, direct buried cables require a greater burial depth than cables installed in conduit. Fourthly, physical barriers. In areas where the emergency system components are exposed to potential physical damage, consider installing physical barriers such as bollards, fences, or concrete pads to protect the equipment. Fifthly, labeling and identification. Clearly label all emergency system components, including wiring, conduit, and equipment, to facilitate identification and maintenance. This labeling should comply with the requirements of the National Electrical Code and other applicable standards. It is also crucial to understand the importance of regular inspection and maintenance. Regularly inspect the emergency system components, including wiring, conduit, and equipment, for signs of damage or deterioration. Promptly repair or replace any damaged components to maintain the integrity of the system. Also, perform routine maintenance on the generator, including testing, lubrication, and fuel replenishment to ensure that it is ready to operate when needed. The NEC provides additional information and requirements related to emergency systems and healthcare facilities. Understanding the nuances of Article 517 is crucial for ensuring patient safety and code compliance. Now let's talk about transfer switches. Transfer switches are critical components of emergency power systems, ensuring a seamless transition between normal power and emergency power during an outage. Understanding the different types of transfer switches and their specific applications is essential for designing and installing a reliable emergency power system. There are several types of transfer switches available, each with its own advantages and disadvantages. Firstly, automatic transfer switches automatically transfer the load from the normal power source to the emergency power source upon detection of a power outage. These switches are typically used in critical applications where even a brief interruption of power is unacceptable, such as hospitals and data centers. Secondly, manual transfer switches require manual operation to transfer the load from one power source to another. These switches are typically used in less critical applications where a brief interruption of power is acceptable. Thirdly, closed transition transfer switches momentarily connect both the normal power source and the emergency power source during the transfer process. This type of switch minimizes voltage and frequency disturbances during the transfer, making it suitable for sensitive electronic equipment. Fourthly, open transition transfer switches interrupt power to the load during the transfer process. This type of switch is less expensive than closed transition switches but may not be suitable for sensitive electronic equipment. When selecting a transfer switch, consider the following factors. Firstly, the type of load being served determine the critical nature of the load and the acceptable interruption time. Secondly, the voltage and current requirements ensure that the transfer switch is rated for the voltage and current of the load. Thirdly, the environmental conditions. Select a transfer switch that is suitable for the environmental conditions in which it will be installed. Fourthly, the available space. Consider the available space when selecting a transfer switch, as some switches are larger than others. Fifthly, the cost balance. The cost of the transfer switch with its features and benefits. Generators are the heart of many emergency power systems, providing a reliable source of backup power during utility outages. Understanding generator sizing, installation, and maintenance is crucial for ensuring a dependable emergency power supply. When sizing a generator, consider the following factors. Firstly, the total load. Calculate the total load that the generator will need to supply, including lighting, equipment, and other essential systems. Secondly, the starting load. Determine the largest motor or equipment that will be started at one time, as this will require additional generator capacity. Thirdly, the voltage and frequency requirements ensure that the generator provides the correct voltage and frequency for the connected loads. Fourthly, the altitude and temperature. Direct the generator capacity for altitude and temperature, as these factors can affect generator performance. Fifthly, the fuel type. Select a generator that uses a readily available and cost-effective fuel source such as diesel, natural gas, or propane. When installing a generator, consider the following factors. Firstly, location. Choose a location that is well ventilated, protected from the elements, and accessible for maintenance. Secondly, ventilation. Provide adequate ventilation to prevent overheating and ensure proper combustion. Thirdly, exhaust system. Install an exhaust system that complies with local codes and regulations and directs exhaust fumes away from occupied areas. Fourthly, fuel supply. Install a fuel supply system that is properly sized and protected from leaks and spills. Fifthly, grounding. Ensure that the generator is properly grounded to prevent electrical shock hazards. Regular maintenance is essential for ensuring the reliable operation of the generator. Perform the following maintenance tasks regularly. Firstly, inspection. Inspect the generator for signs of damage or wear, such as leaks, cracks, or corrosion. Secondly, lubrication. Lubricate the generator components according to the manufacturer's recommendations. Thirdly, filter replacement. Replace the air, fuel, and oil filters regularly. Fourthly, battery maintenance. Maintain the battery in good condition by checking the electrolyte level and charging as needed. Fifthly, testing. Perform regular load bank testing to ensure that the generator can supply the required power. Mechanical protection is vital for all components of an emergency system. This extends to the critical loads themselves. Critical loads are those loads that are essential for the safety and well-being of building occupants during a power outage. These loads may include lighting, life safety systems, medical equipment, and communication systems. Identifying critical loads is the first step in designing an effective emergency power system. Consider the following factors when identifying critical loads. Firstly, life safety systems include fire alarm systems, emergency lighting, and exit signs. These systems are essential for ensuring the safe evacuation of building occupants during a fire or other emergency. Secondly, medical equipment in healthcare facilities. Critical medical equipment such as ventilators, heart monitors, and operating room equipment must be connected to the emergency power system. Thirdly, communication systems. Communication systems such as telephones, radios, and computer networks may be critical for coordinating emergency response efforts. Fourthly, security systems. Security systems such as access control systems and surveillance cameras may be necessary to maintain security during a power outage. Fifthly, lighting. Emergency lighting is essential for providing adequate illumination for building occupants to safely navigate during a power outage. After identifying the critical loads, determine the power requirements for each load. This includes the voltage, current, and power factor. Ensure that the emergency power system is sized to accommodate the total power requirements of all critical loads. Also consider the starting load of any motors or equipment that will be started during a power outage. These starting loads can significantly increase the power demand on the emergency power system. Understanding the NEC requirements is of utmost importance. Section 517.30 of the NEC provides specific requirements for emergency systems in healthcare facilities. These requirements are designed to ensure the safety and reliability of emergency power systems in these critical environments. Key aspects of 517.30 include: firstly, wiring methods. All wiring for emergency systems in healthcare facilities must be installed in rigid metal conduit, intermediate metal conduit, electrical metallic tubing, or other approved raceways. Secondly, separation. Emergency system wiring must be physically separated from normal power wiring to prevent faults or interference. Thirdly, overcurrent protection. Emergency system circuits must be protected by overcurrent devices that are sized to protect the conductors and equipment. Fourthly, testing. Emergency systems must be tested regularly to ensure that they are functioning properly. Fifthly, maintenance. Emergency systems must be maintained in good working condition to ensure their reliability. Staying current with the latest edition of the NEC and any applicable local amendments is crucial for ensuring compliance. Consult with a qualified electrical engineer or contractor to ensure that the emergency power system design and installation meet all applicable requirements.